Hi, my name is Carl Holmgren and I'm gonna give a bit of introduction to FatiStat. We're gonna go through a basic fatigue analysis, probabilistic fatigue analysis using a durability schedule where we use a fairly basic stress life fatigue model. And in order to expedite things, as this is a video with a certain length, I have already created several things that are needed for the durability schedule. And then we see here to the left here, we see some red things, which are time histories, or they're strain time histories. Let's call them loads. And we have in this column, the repeat column, we have for two of these events, event 1 and 2, or events BB or IMP, whatever you want to call them, we have two probabilistic variables that indicate the number of repeats for each event to make up for a complete durability schedule. In the scalar column, we also have two probabilistic variables. They are assigned to events 2 and 3 instead, and they basically stipulate the scale, the coefficient by which we want to scale the load time history of these two events. For one of the repeats, I have not stipulated any probabilistic variable, and neither for one of the scalars, because later on I'm going to assign them constant coefficients instead, so they will not be probabilistic variables. Let's just have a brief look at the strain time histories, and I just mark them just like you would do in Excel or something like that. Hold on the shift button and right click, and up we get a selection of things we can do with these time histories, and one of them is to graph them. So this is the graphing utility, and as we see here we have three time histories in slots 1, 2 and 3. This is the BB time history, the IMP time history, and the RR time history. And each slot to start with shows the first channel of the various time histories. They have more channels, and we can have a brief look at maybe another channel for one of these time histories. So I'm gonna toss, let's say I'll toss this slot 1 and 2. So we'll toss slot 2, and then we'll toss slot 0, and we have this one left here. And then we're going to edit this slot. And this edit window allows us to pick a signal, and we have three different signals to pick from. Those are the ones that were defined in the spreadsheet. And we just want to have a look at another channel of this same time history. So we'll pick that time history again. And here we get the available channels. And as we can see, we actually have 8 channels here. Let's just pick one of them. And we have to pick a color to display this trace with. So here we see we have 2 different channels. We can here clearly see here that it's probably strains these time histories. It's 0.5%. That's the maximum level here, and that's for the worst channel, which is channel 6. All right. So, and then we have the probabilistic variables. FatiStat made the time histories red by default. Then there's nothing we can do about it. Different objects will have different colors and different backgrounds. And to make it easier for us to interpret the spreadsheet, all probabilistic variables will have a green background like this. Let's have a look at these two repeats. So we'll have a look at the probability density function estimate of them. So that's for the BB, and this is for the IMP repeat. Let's overlay them on each other. So we'll toss the bottom slot, and we'll edit the first slot. And here we are going to pick another signal, because we had the BB reps, and now we want to overlay it with the IMP reps. Pick a color. Let's do it, make it green. And here we go. So we see here that the IMP reps is quite a bit higher than the BB ones. It's about 2,300 repeats for that one as an average, and maybe 120 or something for the BB. We can have a bit more detailed look into the definition of these variables. So if I just right click on the BB here, I can edit the probabilistic model. And we see here that it's a log normal distribution with a mean of 120 and a standard deviation of 20. We can do the same with the IMP. Edit it. And we see that's a normal distribution actually. You gotta be a bit careful with normal distributions though, because they can go negative, you know. And the same we have with the scalar. The scalars. Let's have a look at them both. The probability density functions. And here we see that this is most probably log normal distribution, while this is a uniform distribution. Let's overlay them. So I'll do the same here. I'll toss one of the slots, and I will edit this slot and add the RR scalar. And there we go. So we have all the things needed here to create the schedule. I have also added a couple of titles here to make things a bit more easily explainable. And this is basically just comments that you can write in the spreadsheet. So just double click on a cell, and then you can write whatever you want. Enter. I will delete that again. So that's what I've been doing here. Let's create a schedule then. So here we're going to have the schedules underneath. Right click on an empty cell, and you will get all the options of what you can do with an empty cell. And here we are going to create a durability schedule. Before we click this, we have to have created any probabilistic variables. We have to have imported any loads that we are going to be using to compose this schedule, and that we already have. So let's call the schedule, let's be original, schedule 1, and we'll pick our load signals. Everything is done by right clicking pretty much, and then we get all the options that can be used. And in this case we only have 3 time histories, and so those are the options we have to pick from. For the repeats, as we said up here, we are going to use the probabilistic variable of BB underscore reps. And let's see here, yeah, here we have that one. And we're going to use the similar one for the IMP. Here we haven't created anything for event 3. So what we're going to do here is we're going to just put in a constant. So we want to use a repeat of 300 for the RR event. And for the scalar for the BB event, we had neither had created any probabilistic variable, and we just want to scale that one by 1, so it's going to remain unchanged. Let's import the probabilistic scalars. There. Now we have a completely defined schedule. And here it pops up. So just like with the time histories and the probabilistic variables, if we right click on the schedule, we're going to see what we can do with them. And here we can edit, or we can graph it, or we can calculate damage. Let's graph this one. So we have the 3 different events, BB, IMP, and RR. And we have the scalars and the repeats for the various events. The left axis here is applicable for the scalars, and the right one is applicable for the repeats. And we could, for example, entirely exclude the repeats from this plot. And here we go. So now we're just looking at scalars. Let's have a look at the probability density function and the cumulative probability density function for these events for the scalar. That got a bit messy, didn't it? Let's close down the PDF and just look at the CDF. So this is a log normal we can see, and this is a uniform distribution. Let's look at the bars of the repeats here again, and the CDF of those also. All right. We see here for 2 of these coefficients there is no CDF, and that's because they are constants. Hence, they have a CDF that's just a vertical or horizontal line here. These brackets are they represent the plus minus 1 standard deviation. We have more things we can play around with here, axis limits, lin versus log scale, and so on with axis. When we do that, remember that we have to press the update button for the graph to react. There we go. So now we created a schedule. And that's, as we said, is one part that's needed for the fatigue calculation. The second part, of course, is a fatigue model. So we're going to create a very easy simple fatigue model here. It's a plain stress life fatigue model with a constant slope. So let's have a look at what we need to create this. So we right click on an empty cell, and here we see that we can create a stress life model. So the stress life model requires that we know the stress range and the number of cycles for one point of the curve, and that we know the slope, the constant slope in log for the curve. We're going to say that we know these, and we're going to create a probabilistic model just for the slope here. So let's do that first. So we'll prob model for B. Right click, create a probabilistic model, and B is going to be negative, so we cannot use a log normal distribution. We have to use something else like a normal or a uniform. Let's use a mean of minus 0.2 and a small standard deviation of what is it, 0.01. That's 5%, isn't it? We call it B, the probabilistic model name. It took a little bit of time there to after I clicked OK, and that's because it samples a PDF, so we have it available to look at it like that. So an average of minus 0.2. Let's then create the fatigue model. So fatigue models, and right click and create stress life model. We said that we know this already. This is a stress life model, but that doesn't mean that we can't use strains to calculate damage or fatigue life. We basically, instead of using a stress here, we'll just put in the corresponding strain. So we'll say that we know the strain range for 10,000 cycles, and we say that that one is 0.004 maybe, and that is 0.4% strain. And then we right click here on the slope, and lo and behold, we will be allowed to pick probabilistic models. The same would go with these ones here. We can pick a probabilistic model, but we don't have one that we want to use for those. So we pick B, all right, and we call this model first stress life, maybe. That'd be good. So now we have the stress life model here, and we can visualize it somewhat, and we'll display it here. There we go. And as the B was the slope was a probabilistic variable, the stress life distribution will be a distribution. It's not deterministic. However, we said that we knew the stress range or the strain range at 10,000 cycles. Hence, there is no variance there. While when we move away from 10,000 cycles, we get a certain variance due to the variance of the slope B. We're not going to talk more about the actual display here. That's going to be in a separate video later on. So now we know we have both components required for a fatigue analysis. We have a load, in this case a schedule, and we have a fatigue model. So in order to perform a Monte Carlo based fatigue analysis, we will right click on the load and say calculate damage. By doing that, we will be prompted with the available fatigue models, and in this case we only have one model, so we pick that one. And we will also tell the program how many Monte Carlo loops to run. In this case, we say just one of them because it's a video and we don't want to wait forever. So we'll just create one Monte Carlo loop and we'll calculate that. The result will pop up in this cell here. And we're going to have a brief look at that before we look at a larger data set with many Monte Carlo loops. So that will only give me the cumulative damage. So here we have a cumulative damage for the various channels for the complete schedule. I've done something similar. Now let's redo this somewhat. I only picked one loop here, which gave us only one cumulative damage. If I would have picked more than one loop, let's pick two loops and just wait a little bit longer, we're going to get a different kind of result. and it's not going to be just a column of damage values. It's going to be what we call a metadata vector, which includes, here it popped up, which includes let me show you. It includes the outcomes of the variables in the schedule or in the load, and the outcomes of the variables in the fatigue models, plus the damage for the various channels and the life for the various channels for the number of Monte Carlo loops or the number of outcomes. And we can just have a brief look at that data. Basically, where is it? We have one and one point that's hidden. So what we're going to do here is we're going to import a larger metadata vector that actually can be played around with a bit. So it's going to be in the same format as this, and it's going to be for the same schedule. It's just going to be 100 Monte Carlo loops instead. So I will import a native metadata vector. We're going to find it somewhere down here. Schedule 100 loops metadata vector. We'll open that one. And we'll right click on it and we can plot the data. The first plot that shows up here, which is of little interest, it is a scatter plot of the first variable of the metadata vector, which happens to be the number of repeats for event BB. We're going to have a look at a couple of different things that are of interest here that we can study. It might be of interest to see what variables correlate, what input variables, what test schedule variables, and what fatigue model variables correlate with the resulting damage for a certain strain gauge. So we'll remove this slot and we'll add a crossplot slot where we're going to have a look at the damage for channel 1 versus maybe for the scalars of the two events that we actually assign probabilistic variables for. Okay, it looks like the green doesn't much of the green, which is the RR scalar, doesn't have much correlation versus the IMP scalar, which seems to have some correlation. But in order to see this a bit better, we are going to, this is the damage axis, we're going to logarithm or log the damage axis. So we're going to configure this slot, and here are the x-axis settings. We're going to set a new minimum, 0.1 damage maybe, and we're going to log it. We have to press validate here before we press OK to make sure that our settings are valid. And here we see that almost a straight line in loglin, which means of course that the IMP scalar has a great effect on the damage. And we can do the same thing with the fatigue model variables also. Another thing that's of great interest is to try to determine at what percentage of a complete durability schedule can we expect a certain percentage of the specimens to have failed. So we're going to try to see here for gauge 1, for example, at what percentage of the test has 10% of the specimens failed, or we can look at it like are 90% of the specimens still alive. So we'll remove the slot, and we'll add a cumulative density function slot. And we only have one signal, of course, only one metadata vector. And we look at life. We'll assign a color, green maybe, like this. All right. So we see here that we had 100 outcomes. 10% is, of course, 10 outcomes. So somewhere down here in this region, 10% of the outcomes have failed. Let's refine this plot a little bit. I right-clicked on it, and we are going to increase the number of bins to 64 instead. A little bit better. Still a bit hard to see down here. And so we're going to go ahead and zoom in here between 0 and 0.5%. We're going to configure the plot. We're going to configure the x-axis. Our minimum is 0 and our maximum is 0.005. Validate. OK. And let's increase the number of bins. Okay. So at 10% failures, we see the x-axis here, or the life axis, reads 2.25%. So basically, at 2.25% into the test, there we are. But 2.3% into the test, 10% of our specimen have failed, or we have a survival rate of 90%. And there we go. I think that was the introduction. There are other videos available for more detailed setup of fatigue models, and another one of the graphing utility. And I hope you enjoyed it, and talk to you guys later.